The exponential distribution is the most important continuous distribution. Remember that for the exponential distribution, the PDF is 1 over lambda e to the power negative lambda x, the expected value is lambda, and the variance is lambda squared. So suppose we have a joint distribution where both x and y are exponential, where the means are both equal to 3. Let's find the probability that the sum is less than or equal to 6. Since x and y are independent and exponentially distributed with means 3, then the probability density function will be the product of the two exponential distributions. And we want to find the probability that x and y are in some region. So that'll be our double integral over the region. And since we want to do this integration in the hardest way possible, we won't graph anything. Wait, maybe we should graph something, so we'll go ahead and graph that region. Now our boundary is going to be the line x plus y equal to 6, and since we want to be less than or equal to 6, we want to be in this triangular region here. There doesn't seem to be any preferred direction of integration, so we'll integrate with respect to y first and then x, and so our integral will be which we can evaluating the first integral, then evaluating the second integral, and remember, intuition is insightful. Remember that the mean of an exponential distribution tends to be higher than the median. So if the mean of x is 3, more than half the values of x are less than 3, and likewise, more than half the values of y are less than 3. So on some level, we'd expect that more than half the values of their sum will be less than 6, and that's consistent with our result. Or let's consider a different situation. Suppose a device has a lifetime that's exponentially distributed with a mean of 6 hours, and a backup device is independently and exponentially distributed with a mean of 2 hours. Let's find the probability the device will still be working in 12 hours. So we want to find the probability that the sum is greater than or equal to 12. And since x and y are independent, this is the product of the two probabilities, so our relevant PDF is going to look like, and we want to find the probability over some region. So again, let's go ahead and graph that region, and we'll also include our boundary line. Now, our region is actually this outer region here. But if we integrate along y first, our lower boundary is sometimes the line and sometimes the x-axis. And if we integrate along x first, our left boundary is sometimes the line and sometimes the y-axis. Since every boundary curve change requires a new integral, finding the probability directly is going to take more effort. So what if we find the complementary probability instead? And so we want to find the probability that x plus y is less than 12, which is over some other region. And again, there doesn't seem to be any preferred direction of integration, and so our integral will be, which we evaluate as, and remember we're looking at the probability that x plus y is greater than or equal to 12, so that's the complementary probability, which will be, and again, we might check with our intuition, because the devices have mean lifespans of 6 and 2 hours, then we'd probably expect a mean of something less than 8 hours, so it seems unlikely that the device would still be working after 12 hours.